Today, we're going to examine a central paradox in rammed earth construction, based on some ideas in the book The Memory of Rock, Understanding Rammed Earth by Gokul Salvadi. The core subject is the contradictory role of water, how it acts as both the agent of creation and at the same time, the primary force of destruction.
And really, the entire practice of building with rammed earth hinges on understanding this. It's a dualistic relationship. Water is the essential medium you need for construction, but it's also the very same erosive force that the finished building has to contend with for its entire life.
So first, let's look at water's role in just forming the wall. It's the element that makes the consolidation of earth possible in the first place, but, and this is key, only when it's present in a very specific and narrow range.
Well, think about what happens if you try to build with earth that's too dry. The particles just don't bind together. They scatter under the force of the tamper, and, well, nothing happens. You get no consolidation. Now, on the other hand, if the soil is too wet, it just becomes mud. The tamper sinks in and displaces the material instead of compacting it.
So, somewhere between those 2 points of failure, there's a state that soil mechanics calls the optimum moisture content. This is that precise point where there is just enough water, and no more, for the soil particles to achieve their maximum possible density when they're compacted.
At this optimum level, water is actually doing three distinct things all at once. First, it's a lubricant. It creates this very thin film around the soil particles that lets them slide past one another and settle into a really dense arrangement. Second, it activates the clay platelets, which gives them a kind of electrostatic charge that creates cohesive bonds, sort of a natural glue. And finally, it fills the little voids between particles, which allows the force of the rammer to be transmitted evenly through the whole mixture. And then, once the compaction is done, this water just evaporates, leaving behind a solid, dense wall.
On a construction site, builders develop this very tactile sense for that perfect moisture window. They use methods like the hand test. You squeeze a ball of earth, and it should hold its shape. It should break cleanly when you push it with your thumb, and then it should fragment into just a few large pieces when you drop it. It's a learned skill, and it's all about managing water to create the wall. But once that's done, the entire design philosophy shifts to managing water to preserve it.
So once the wall is built, and that initial construction water has left, any new water that arrives becomes an adversary. And the building's design has to anticipate this right from the very beginning.
The main defense against erosion from rainwater isn't some chemical additive in the material itself. It's a fundamental design feature, a proper roof overhang. You could call it a good hat. And its dimensions are calculated based on the local climate, specifically to keep falling water off the vertical face of the wall.
Now, from below, the threat is ground moisture, which can be drawn up into the wall through capillary action, almost like how a plant draws water up from the soil. So the foundation's primary job is to provide separation. It acts as an impermeable barrier, a good boot, that keeps the base of the wall permanently dry.
Now, if a protective coating is put on the wall, its properties become absolutely critical. A traditional lime plaster, for example, is vapor permeable. It resists liquid water, but it allows any vapor that might be trapped inside the wall to escape. A modern cement plaster, on the other hand, is impermeable. It actually traps that internal moisture, and that can build pressure, it can cause the plaster to delaminate, and ultimately weaken the wall behind it.
This quote really points to a core difference in material philosophy. Rammed earth is designed to yield and respond to forces like moisture. It has to breathe. Concrete, by its nature, is engineered to rigidly resist those forces. And that resistance is effective, but only up to its breaking point, where failure can be sudden and it can be complete. It's just a fundamentally different approach to what durability means.
So this responsiveness to water, which on the surface seems like a vulnerability that you have to design around, is also the very mechanism behind the material's performance advantages in a finished building.
Rammed earth walls are what's known as hygroscopic. The clay within the soil mix has this natural ability to attract and hold on to water molecules directly from the air. This constant, passive interaction with airborne moisture is really the key to how the interior space feels. This hygroscopic property is what allows the walls to buffer indoor humidity. So, on a humid day, the clay surfaces absorb excess moisture right out of the air, making it feel less damp, and on a dry day, they release that moisture back into the air. This process of adsorption is also what's called exothermic, which means it releases a very small amount of heat. It's subtle, but it can make an interior feel perceptibly warmer and drier during, say, a monsoon season. And then beyond humidity, the sheer mass of the walls acts as a kind of thermal battery. They absorb the sun's heat on the outside surface during the day, but it takes many hours for that thermal energy to actually conduct all the way through the wall's thickness. This creates a really significant time lag.
And the practical effect of this can be an interior temperature that is 8 to 10 degrees cooler than the peak outside temperature. The heat that the wall absorbed at noon might only reach the interior surface late in the evening, which is right about the time you can vent it out of the building with cool night air. This provides a kind of passive cooling and a pretty significant reduction in the energy needed for climate control.
So the relationship with water is this continuous cycle. It's used to make the wall, it's defended against to protect the wall, and finally, it's allowed to interact with the finished wall to give the structure its living, buffering quality. The material functions not by creating some inert barrier, but through a constant, managed exchange with its environment.